Hello, my name is Isabella Rangos, and this is my Lab 3 video report, The Magnetic Field of a Bar Magnet. In this lab, we explore the magnetic field produced by a cylindrical bar magnet. Using a smartphone app, I measured how separation distance affects the magnetic field, and used this to determine the distance dependence factor and magnetic moment. I use these observations and calculations to show that as the magnetometer moves closer to the magnet, the measured X component of the magnetic field increases. The fundamental physical principles involved in this lab experiment include the Biot-Savart law, the distance dependence equation, and the linearized version of this equation. After completing my experiment, I filled out the spreadsheet with the according values. Above, you can see the on-axis and off-axis values. After linearizing my results from the observations on the previous slide, this is my final graph. Using the y-intercept and the slope of this graph, I was able to calculate the magnetic moment. The distance dependence factor is the slope of this graph. These are the numerical results that I calculated from my previous observations. Following completion of my physical experiment, I then began my computational model. I first began by writing a function to calculate the magnetic field of the inputs. I then altered several sections of the code to reflect my observations and calculation values, including mu, or the distance dependence factor, the b-scale, the distance, and the d perpendicular value. I then began to code my arrows, first altering the vectors for the distances on the axis and at the perpendicular locations. I then edited the code for the 2 arrows on axis and the 4 arrows perpendicular. These arrows were reflected in my computational model based off of the inputs that I coded earlier. Here is the final result of my computational model with the outputs on the bottom and the image result on the top. The d is very similar to the distance I have measured from my physical experiment. At the very bottom, you can see the predicted magnetic field at 45 degrees. I then compared this value to my observed B at 45 degree value from my experiment. These values differ slightly, but are in the same 10th power. The exact values of the x and y coordinates differ, perhaps due to magnetic interference during the physical experiment. Despite varying slightly, these are fairly close results considering the small degree to which they were measured. What if we did not orient our experiment to compensate for the magnetic north? In this case, our results would be inaccurate. The calculations would include Earth's magnetic field, and it would not be an accurate assessment of the magnet and the magnetic field that we were using and calculating. What if we stuck 2 identical magnets together and repeated the experiment? In this case, our measurement values would increase. Because we doubled the magnetic field, we would have a greater force as a result. In conclusion, we have been able to determine that as the magnetometer moves closer to the magnet, the measured X component of the magnetic field increases. We've seen that the magnetic field's predicted and observed values differ, but are within reasonable range for this experiment. We can also create a computational model showing the magnetic field around the bar magnet based on our observations both on and off axis using the bar magnet in our experiment.